Think about the most impressive structures around you. Towering skyscrapers, massive bridges. They all share one crucial foundation, the ground beneath them. But that seemingly simple earth is, well, surprisingly complex. And for centuries, how to build safely on it was a real puzzle. That's where geotechnical engineering comes in.
Exactly. And in this deep dive, we're going to explore the fundamental ideas behind how we understand and work with soil. We'll be drawing insights from HUTUM 101 principles of geotechnical engineering to unpack, well, everything from where soil comes from to how it behaves when we build on it. So whether you're an engineer facing a tricky soil problem or maybe just curious about why the ground holds us up, there's a lot to uncover.
And it sounds like a very practical field. You mentioned the variety of units used. We're talking pressures and things like newtons per square meter or kilometer mat and weights in pounds per cubic foot.
Absolutely.
It really shows how hands-on this area of engineering is. Okay, so let's get started right at the beginning. What's the story of soil itself? Where does it come from?
Well, the story begins with rocks. All sorts of rocks, actually. Think of the rock cycle as this ongoing transformation. You have igneous, sedimentary, and metamorphic rocks constantly changing form. Igneous rocks are essentially born from molten rock, cooling either on the surface after a volcano erupts or solidifying deep underground.
Okay, so we start with these solid masses of rock. But they don't just stay like that, right? Something has to break them down to eventually become the soil we know.
That's right. That's where weathering comes in. It's the process of these rocks being broken down into smaller and smaller pieces. And there are two main ways this happens. First, you've got mechanical weathering.
Physical breakdown.
Exactly. The physical breaking apart of rocks, things like cycles of freezing and thawing water cracking rocks, or, the relentless force of wind and waves grinding them down. You see incredible examples of this mechanical erosion shaping coastlines like Yelyu and Taiwan.
Yeah.
The ocean and wind have sculpted these amazing rock formations there.
Wow. And the other type?
The other type is chemical weathering. This actually changes the chemical makeup of the rocks, causing them to decompose. It's a chemical reaction.
Right. And this whole breakdown process, it leads to different kinds of soils depending on whether these fragments stay put or get moved around.
Precisely. Residual soils are those that form right there, where the original rock weathered. A key thing about these is that you often see a gradation of particle sizes, finer particles at the top, and then coarser, even angular bits of the original rock as you dig deeper.
Makes sense.
Transported soils, on the other hand, are moved from their original location. Things like glaciers, rivers, wind, or even gravity pick them up and deposit them somewhere else.
Now, the starting point isn't just those fiery igneous rocks, is it? You mentioned sedimentary and metamorphic are also part of the story.
Yes, absolutely. Sedimentary rocks are formed from the accumulation and then cementing together of sediments. This can happen in a couple of ways. You've got clastic processes, which involve fragments of older rocks being deposited and then compressed and bound together. Then there are chemical processes. This happens when minerals dissolved in water precipitate out and solidify.
Like limestone.
Exactly, like how limestone often forms from calcium carbonate, or how rock salt and gypsum crystallize as seawater evaporates. And it's interesting to think about what these rocks are made of at a mineral level. Calcite in limestone, halite in rock salt.
So all this grinding, weathering, chemical transformation, it eventually leads us to really fine particles, clay. And I understand there are specific types of clay minerals that give soil that characteristic squishy, moldable feel when it's wet.
That's exactly right. Clay minerals like kaolinite, elite, and montmorillonite. They're formed through the chemical weathering of other minerals like feldspars and micas. These tiny plate-like particles plus the electrical charges they carry are what give clay its plasticity.
Plasticity. That ability to be shaped when wet and hold that shape.
Precisely.
Okay, so we know where soil comes from now. But if we're an engineer trying to build something, how do we actually analyze these different size bits that make up the soil?
Right. To figure out the makeup of a soil, we use something called mechanical analysis. This involves two main tools, sieves for the larger particles and a hydrometer for the really fine ones.
Sieves seem pretty straightforward, like sifting flour but with soil.
Sort of, yeah.
Yeah.
Sieve analysis is pretty straightforward. You pass the soil through a stack of screens with progressively smaller openings. This tells you the range of sizes present in the coarser part of the soil. It gives you the intermediate dimensions of the particles.
And for the really, really tiny stuff, the silts and clays, that's where the hydrometer comes in.
Correct. Hydrometer analysis helps us understand the distribution of those fine-grained particles. It works on the principle that smaller particles settle more slowly in water than larger ones. It's based on Stokes' law, fundamentally. So a hydrometer, Often a specific type, like an ASTM 152H, is used to measure the density of a soil-water mixture at different times. By seeing how the density changes as particles settle, we can calculate the effective diameter of these tiny particles. Think of it as the diameter of a sphere that would settle at the same rate.
An equivalent sphere diameter.
Exactly. There's a measurement called the effective depth, L, which is the distance from the water surface down to where the hydrometer is measuring the density. This depth changes as sediment settles, and there are charts, like Table 2.7 in the reference, that relate the hydrometer reading to this depth.
So we run these tests, the sieve and the hydrometer, and then we end up with a bunch of numbers about particle sizes.
Yeah.
How do we actually make sense of all that data?
Well, the results are usually plotted on a graph. It's called a particle size distribution curve. This curve shows you what percentage of the soil particles are smaller than any given size.
And we can pull useful numbers from that curve.
Yes, some really important numbers. One key one is the effective size, also known as D10. This is the particle diameter at which 10% of the soil by weight is finer. It gives us a good indication of things like hydraulic conductivity, how easily water moves through the soil.
And there are other parameters too, right, that
Yeah.
tell us about the range of sizes, like how uniform the soil is.
Exactly. The uniformity coefficient, Q, that's calculated by dividing the D60 size, the size where 60% is finer, by that D10 size.
Okay, Q equals D60 over D10.
Right. A higher Q means the soil has a wider range of particle sizes. It's less uniform, or what we call well-graded. Then there's the coefficient of gradation, CC, that involves the D30 size as well. The formula is D30 squared divided by D60 times D10.
Uh-huh.
This tells us about the shape of the curve, whether it's smooth or if there are maybe gaps in the particle sizes.
And why are these coefficients Q and CC so important?
They're really important for things like drainage and compaction. A soil with a good mix of particle sizes, a well-graded soil, which usually has a CC between 1 and 3, tends to have smaller spaces between the larger particles filled by smaller ones.
So it packs together better.
It can, yes. And that can actually make it less permeable, less easy for water to flow through compared to a uniformly graded soil where all the particles are roughly the same size, leaving larger, more connected voids.
Interesting. Okay, we've talked a lot about the size of the particles. What about their actual shape? Does that matter? Are they round, jagged, flat?
Absolutely. The shape plays a significant role in how the soil behaves. We generally categorize shapes as, say, rounded, angular, or flaky.
And how does shape affect things?
Well, rounded particles, they tend to pack together more easily, which might lead to denser soils under certain conditions. Angular particles interlock more.
Like little puzzle pieces.
Sort of, yeah. That interlocking gives the soil greater shear strength. Flaky particles, like many clay minerals, have a very large surface area relative to their volume. This greatly affects how they interact with water and other particles, influencing plasticity and swelling.
But measuring shape is harder than measuring size.
Much harder to quantify, yes. So it's often considered in a more qualitative way during analysis.
Okay, so we have an idea of what the soil's made of, particle sizes, shapes. But how these particles are arranged together in the ground, the voids, the water, that must also be critical. Let's talk about these weight-volume relationships.
Yes, understanding how the different components of soil, the solid particles, the water, and the air-filled voids relate in terms of their weight and volume is absolutely fundamental. We
Yeah.
use a few key terms here. The void ratio, E. That's the ratio of the volume of the empty spaces, the voids, to the volume of the solid particles themselves.
Okay, volume of voids over volume of solids.
Right. Then there's porosity, N. That's the ratio of the volume of voids to the total volume of the soil. They're related, of course.
Got it.
The degree of saturation, S. That tells us what percentage of those void spaces is filled with water. Ranges from 0 for dry soil to 100%, or 1 for fully saturated soil.
Water content, W.
That's the ratio of the weight of the water to the weight of the solid particles, usually expressed as a percentage.
Specific gravity, Gs.
Gs compares the density of the soil solids to the density of water. It's dimensionless. For most soils, it's around 2.6 to 2.8.
And finally, unit weight.
Right. Unit weight, GAMED, is the total weight of the soil per unit volume. Includes solids and water. And dry unit weight, GAMED, is the weight of only the solid particles per unit total volume.
It's quite a list of terms.
Yeah.
And I know there are formulas that connect all of these, which must be useful.
Yes, there are some really powerful formulas that link these properties. For example, a very common one relates dry unit weight, specific gravity, the unit weight of water, and void ratio, GAMED at 1 plus E. Another one connects unit weight, water content, and dry unit weight by exists, U, 1 plus W. And you can relate porosity and void ratio. N equals E, 1 plus E, and E equals N, 1N.
So if you can measure a few of these, you can calculate the others.
Exactly. These relationships are incredibly useful. Chapter 3 of the textbook, for instance, has lots of example problems that walk you through these calculations. It really helps make these concepts concrete.
It sounds like being able to work with these relationships is absolutely key to understanding the current state of a soil in the ground. Now let's switch gears a bit and talk about something that's really characteristic of fine-grained soils, especially clays. Plasticity. You mentioned it earlier.
Yes, plasticity. It's a really important property that describes how a cohesive soil, like clay, behaves when the amount of water in it changes. We use what are called the Atterberg limits to define these different states of consistency.
Atterberg limits, like thresholds.
Exactly. Thresholds of water content. The main ones are the liquid limit, LL, the plastic limit, PL, and the shrinkage limit, SL. These limits are essentially the moisture contents at which a cohesive soil transitions from one type of behavior to another, say, from liquid to plastic, or plastic to semi-solid.
So the liquid limit, that's the point where the soil starts to act almost like a thick liquid.
That's a good way to think about it, yeah. Technically, the liquid limit is defined as the moisture content at which a soil will just begin to flow when a very small shearing force is applied. The standard lab test for this uses a device called a Cassegrain cup.
Cassegrain cup, right?
You put a pad of soil in the cup, cut a standard groove in it, and then the cup is repeatedly dropped from a standard height of 10 millimeters.
Okay.
The liquid limit is the moisture content at which that groove closes up over a half-inch distance after exactly 25 drops. In practice, you usually run the test at several different moisture contents and get different numbers of drops. Then plot moisture content versus the log of the number of blows.
Oh, the flow curve.
Right, the flow curve. And the moisture content corresponding to 25 blows on that curve is your liquid limit. Figures 4.3, 4.4, and 4.5 in the textbook show the equipment and the process. The slope of that flow curve is called the flow index, by the way.
Okay, that's the liquid limit. Then we have the plastic limit, PL. What's happening with the soil at that point?
The plastic limit is the moisture content at which the soil just starts to crumble when you try to roll it into a thin thread.
How thin?
About 1/8 of an inch, or 3.2 millimeters, in diameter. This marks the lower boundary of the plastic state. It's the point where the soil is still moldable but will start to fall apart if you try to work it any drier or thinner. The test involves repeatedly rolling a small piece of soil on a glass plate until it reaches that critical diameter and starts to break into segments. Figure 4.7 shows this.
And the difference between these two limits, the liquid limit and the plastic limit, gives us another important value, right? Yeah.
Exactly. The plasticity index, PI. You calculate it simply by subtracting the plastic limit from the liquid limit. PI equals LL/PL. The PI is a direct measure of the range of moisture content over which the soil behaves plastically.
So a higher PI means it stays plastic over a wider moisture range.
Precisely. A higher PI means the soil has a wider range of moisture contents where it can be deformed without cracking or crumbling. This index is incredibly useful for classifying clays and predicting how they'll behave in engineering applications, things like shrink swell potential.
And that leads us to the famous plasticity chart, often called the Cassegrain chart. I've definitely heard engineers talk about plotting soils on that.
Yes, the plasticity chart, which you can see in figure 4.1, is a fundamental tool for classifying fine-grained soils, the clays, and silts. It's a graph where you plot the plasticity index, PI, on the vertical axis against the liquid limit, LL, on the horizontal axis.
And it's divided into zones.
Right. The chart is divided into different zones by key lines. The most important is the A line, which has a specific equation. PI equals 0.73 times LL20. This A line generally helps separate the more clay-like soils, which plot above it, from the more silt-like and organic soils, which plot below it.
Okay.
There's also the U line, another boundary defined by PI equals 0.9 times LL8. This represents the approximate upper limit of where natural soils typically plot. If your test results plot way above the U line, it might suggest an error in the testing.
So by seeing where a soil's LL and PI fall on this chart, engineers can classify it.
Exactly. They classify it as a clay C or a silt M, and then further categorize it based on its liquid limit as low plasticity L. medium or intermediate plasticity I, or high plasticity H. For example, CH means a high plasticity clay.
Very systematic. You also mentioned this idea of activity when talking about clay earlier. What does that tell us?
Activity. Activity is a way to gauge the potential for volume change, swelling, and shrinking in a clay soil relative to the amount of clay minerals present. It's calculated by taking the plasticity index, PI, and dividing it by the percentage of clay-sized particles, those smaller than 0.0002 millimeters in the soil.
So PI divided by percent clay fraction.
Right. A clay with a higher activity value will generally tend to swell more when it gets wet and shrink more when it dries out. It relates back to the type of clay mineral present. Montmorillonite, for instance, is very active.
Okay, so we've looked at individual particles and their plasticity. Now, how do these particles actually arrange themselves when they're just sitting there in the ground? Let's talk about soil structure.
Right, soil structure. This refers to how the soil particles are arranged in space and the forces that hold them together. It's really about the fabric and the interparticle forces. We talk about the soil fabric, which is the geometric arrangement of the particles, and the structure includes the forces between them.
And this differs between coarse soils like sand and fine soils like clay.
Yes, definitely. In coarser soils like sands and gravels, we often talk about single-grain structures where the particles are mainly in direct contact, held by gravity and friction. In finer sands and silts, you can sometimes get what's called a honeycombed structure, especially if they were deposited gently, say in water. Particles form loose, arch-like arrangements with relatively large void spaces. Figure 4.20 shows an example.
Honeycombed sounds unstable.
It can be, yes. It can collapse if disturbed or loaded. Thinking about packing, even with perfect spheres, the loosest possible packing gives a void ratio around 0.91, while the densest is about 0.35. Real soils with their irregular shapes and sizes fall somewhere in between or even outside that range for honeycombed structures.
And for clays, the structure seems like it would be way more complex because of those electrical forces between the tiny plate-like particles we talked about.
Exactly. The structure of clay soils is heavily influenced by the electrochemical forces at the particle level. Remember, the edges of clay particles can have positive charges, while the flat surfaces often have negative charges. This leads to both attractive and repulsive forces depending on how they orient.
So they attract and repel each other.
They do. When clay is first mixed with lots of water and the particles are far apart, the repulsive forces tend to dominate, resulting in a dispersed structure where the particles try to stay parallel but separate, like in figure 4.21a. However, in natural marine clays especially, where there are electrolytes in the water, the attractive forces can dominate, leading to a flocculated structure. Particles stick edge to face or edge to edge, forming a kind of cardhouse structure, also shown in figure 4.21a.
Flocculated, like clumps.
Kind of, yeah. And it gets even more complex. In many natural clay deposits, there's a hierarchy. Particles form little parallel groups called domains. These domains then cluster together, and these clusters can aggregate further to form PEDs, which are larger structural units you might even see with the naked eye, often separated by cracks or fissures. Figure 4.22 shows this idea.
Wow, domains, clusters, PEDs. Quite a structure.
It is, and this hierarchical structure has a big impact on the clay's strength, compressibility, and permeability.
Okay, we've got a good understanding now of what soil is, its properties, and how it's structured naturally. Now, in construction, we often need to change the properties of the soil, right? Make it stronger, denser. One key way is through compaction. Why is compacting soil so important?
Soil compaction is a really crucial process in construction. Essentially, it's about making the soil denser and more stable by pressing the soil particles closer together. By forcing air out of the void spaces, we increase the soil's unit weight, which in turn reduces how much it will settle under load, increases its shear strength, and decreases how easily water can flow through it.
So better support, less sinking, less water getting through.
Exactly. All of this makes the soil a much better base for supporting structures like buildings, roads, embankments, dams, pretty much anything we build on the ground.
And there are standard tests we use in the lab to figure out how well a particular soil can be compacted, right? Like the Proctor test.
Absolutely. The Proctor test is the classic. The standard Proctor test, ASTM D698 is the common designation, is a laboratory test that helps us determine the optimum moisture content at which a soil can be compacted to its maximum dry density using a specific amount of compaction energy.
How does it work?
Well, the test involves taking a sample of soil, mixing it with a certain amount of water, and then compacting it in a standard-size mold using a hammer of a specific weight, 5.5 pounds, dropped from a specific height, 12 inches. This is done in 3 layers with 25 blows per layer.
Okay, very specific procedure.
Very specific. For each test run, you use a different moisture content. After compaction, you measure the weight of the soil in the mold and its moisture content, and then you calculate the resulting dry unit weight. Equation 6.2 in the book shows the basic calculation.
And you do this for several moisture contents?
Yes. You repeat the test several times with different moisture contents, and then you plot the calculated dry unit weight against the moisture content. You get a curve, typically sort of like an upside-down U. Figure 6.3 shows what it looks like.
And the peak of that curve is the sweet spot.
Exactly. The peak of that curve tells you the maximum dry unit weight you can achieve for that particular soil with that specific compaction effort, and the corresponding moisture content is called the optimum moisture content, WOPT.
And I remember seeing that if you put more energy into the compaction process, maybe hit it harder or more times, that curve actually shifts.
That's right. If you increase the compaction effort, for example, by using a heavier hammer, like the 10-pound one used in the modified Proctor test, ASTM D1557, or dropping it from a greater height, 18 inches in the modified test, or using more layers or blows, the whole moisture density curve shifts upward and generally to the left.
Upward and leftward, meaning?
Meaning you can achieve an even higher maximum dry unit weight, but you'll typically need slightly less moisture, a lower optimum moisture content, to reach that peak density. Figure 6.6 illustrates this effect clearly. The standard Proctor test imparts about 600 kilonewton of energy, while the modified Proctor test is much higher, around 2,700 kilonewton.
So different energy levels for different project requirements.
Precisely.
Okay, that's the lab test. So out in the field, when they're actually building a road or foundation pad, how do they compact the soil? What kind of equipment do they use?
Well, there's a whole range of compaction equipment available, and the best type to use really depends on the type of soil you're working with and the specific job requirements.
Like different tools for different soils.
Exactly. For granular soils like sands and gravels, smooth wheel rollers, figure 6.15, are often effective. They provide static weight. They're also good for proof rolling, basically checking the stability of a finished layer. Pneumatic rubber-tired rollers, figure 6.16, with several rows of tires, are more versatile. They use both pressure and a kneading action, so they can work well on both granular soils and finer grain soils like silts and clays.
And those rollers with the funny feet.
Ah, the sheep's foot rollers, figure 6.76. They have these protrusions, or feet, on the drum. They're particularly effective for compacting cohesive soils like clays. The feet penetrate the loose layer and compact the soil from the bottom up.
Okay.
And then there are vibratory rollers. These use vibration in addition to static weight, which is very efficient for densifying granular materials like sands and gravels. The vibration helps the particles rearrange into a denser state.
What if you need to compact soil that's deeper down, not just the surface layers?
Good question. For compacting deeper layers, we might use methods like dynamic compaction. This involves dropping very heavy weights, like several tons, from significant heights, maybe 10 to 30 meters. The impact energy compacts the soil over a considerable depth.
Dropping massive weights sounds impressive.
It is. Engineers have even developed empirical equations like 6.2 and 6.21 to estimate the significant depth of influence based on the weight and drop height. Another method, particularly good for loose sandy soils, is vibroflotation. This uses a large vibrating probe called a vibroflot that's inserted into the ground. Sometimes water jets are used too. The vibrations densify the surrounding soil. Vibroflotation works best for soils within a specific range of particle sizes, roughly zone 1 in figure 6.34.
Okay, so various ways to densify the soil. We've made the soil denser by compacting it. Now let's think about the water that's in the soil and how it moves. That brings us to the idea of permeability, right? Yes, permeability. Or, more formally, hydraulic conductivity. We often use the symbol K. It's a measure of how easily a fluid, usually water, can flow through the interconnected void spaces in a soil or rock.
And why is this important?
Oh, it's critical in many areas of geotechnical engineering. Think about designing drainage systems for roads or foundations, analyzing how water seeps through or under dams, predicting how quickly contamination might move through the ground with groundwater flow, or figuring out settlement rates in clays.
So it affects stability, drainage, contamination, lots of things. What are the typical units?
The units for hydraulic conductivity are actually units of velocity, like meters per second, centimeters per second, or maybe feet per day.
Velocity. That seems odd for a property of the soil.
It comes from Darcy's law, which is the fundamental rule governing this flow. at least under many conditions.
Darcy's law. What does that say?
Darcy's law, often written as V or Q key equals key, see equation 7.6, states that the apparent flow velocity through a porous medium like soil is directly proportional to the hydraulic gradient. That's the slope of the water pressure.
Essentially, yes. It's the change in total head, which includes pressure head and elevation head, per unit distance of flow. So a steeper gradient means faster flow, assuming K stays constant. The K is the constant of proportionality, the hydraulic conductivity.
But you said under many conditions. Does Darcy's law always apply?
Good point. It works very well for most laminar flow conditions in sands and gravels. However, it has limitations. For very high flow rates in coarse materials, the flow might become turbulent, and Darcy's law doesn't hold. More importantly, for fine-grained soils like clays, when the hydraulic gradient is very, very low, the relationship between flow velocity and gradient might not be perfectly linear anymore. There might be a minimum threshold gradient needed to initiate flow. Figure 7.4 shows this deviation at low gradients.
Okay, so what are the main things that actually affect how permeable a soil is? What determines K?
Several factors come into play. The size and shape of the soil grains are huge. Coarser soils like sands and gravels have larger interconnected void spaces, so water flows through them much more easily. They have high K values. Fine-grained soils like silts and clays have tiny pores, making flow much slower, low K values.
So grain size is number one. What else?
The void ratio is also important. Generally, a higher void ratio means more space for water to flow, leading to higher permeability, assuming those voids are connected. The properties of the fluid itself matter to primarily its viscosity. Water viscosity changes significantly with temperature. Colder water is more viscous and flows more slowly.
Temperature matters.
It does. And finally, the tortuosity of the flow paths. The water doesn't flow in a straight line. It has to wind its way around the soil particles. More tortuous paths mean lower effective permeability. For clays, the structure and interaction with clay minerals also play a big role.
I know engineers sometimes need to estimate permeability. Are there quick ways to do that, maybe based on grain size?
Yes, especially for granular soils, there are empirical relationships that try to estimate K. One of the oldest and best known is Hazen's equation, which relates K primarily to the effective grain size, D10. It's roughly K, CMS equals C, D10 in millimeters too, where C is a constant.
Useful for sands. What about clays?
It's much more difficult to come up with reliable empirical equations like that for cohesive soils. The pore structure in clays is far more complex, and factors like the arrangement of clay particles, fabric, the chemistry of the pore water, and the interaction between water and the charged clay surfaces play a significant role. Research comparing experimental results with various theoretical or empirical equations often shows a lot of scatter for clays, as you can see in figures like 7.11. Lab or field tests are usually needed for clays.
Okay, now what happens if you don't have just one uniform soil layer? What if you have layers of different soils, like sand over clay? How do you figure out the overall permeability of that whole system?
That's a common situation. When you have layered soils or stratified soils, the overall or equivalent hydraulic conductivity depends crucially on the direction the water is flowing relative to those layers.
Parallel versus perpendicular flow.
Exactly. If the water is flowing parallel to the bedding planes of the layers, the overall permeability is essentially a weighted average of the permeabilities of the individual layers, weighted by their thickness. The water tends to preferentially flow through the more permeable layers.
Makes sense. And if it flows across the layers?
If the water is flowing perpendicular to the layers, it has to pass through each layer in sequence. In this case, the overall permeability is dominated by the least permeable layer. The calculation involves a different kind of average, called the harmonic mean. The equivalent K for perpendicular flow is always less than for parallel flow.
So the equations are direct.
Yes, the specific equations for calculating these equivalent permeabilities, KHEQ for horizontal parallel and KVEQ for vertical perpendicular, are given in Chapter 7. Example 7.12 and Figure 7.20 provide a good illustration of how to calculate these for a soil profile with multiple distinct layers.
All right. We've talked about water flowing through the soil. What happens when that flow becomes significant, maybe under a dam or into an excavation? That leads us to the idea of seepage, right,
Oh.
and potential problems.
Yes, seepage is simply the term we use for the flow of groundwater through the soil, particularly when we're analyzing its effects on engineering structures. Understanding seepage is really important for analyzing the stability of things like earth dams and retaining walls, figuring out uplift pressures on foundations, and predicting potential problems like soil erosion or even a complete loss of strength in certain situations.
And how do we analyze this seepage? I've heard of flow nets.
Flow nets are a classic graphical tool used to visualize and analyze two-dimensional, steady-state groundwater flow through a porous material like soil. Figure 8.3 shows a typical example. They're based on the assumption that the soil is homogeneous and isotropic, although they can be adapted for anisotropy.
How do engineers actually create and then use these flow nets? What are the lines showing?
Flow nets are made up of two sets of lines that ideally intersect at right angles, forming approximate squares in isotropic soil. First, you have flow lines. These show the paths that individual water particles would follow as they move through the soil, say, from the upstream side of a dam to the downstream side. Water doesn't flow across a flow line.
Okay, the water's path and the other lines.
The other set are equipotential lines. These connect points within the soil that have the same total head, that is, the same energy level, combining elevation and water pressure. There's no flow along an equipotential line. Flow is always perpendicular to them.
So lines of equal energy.
Exactly. The flow of water itself is governed by a fundamental mathematical equation called Laplace's equation of continuity, which applies to potential flow problems like this. By carefully sketching these flow lines and equipotential lines, making sure they intersect at right angles and form roughly square shapes, engineers can do two main things.
What are those?
First, they can calculate the rate at which water is seeping through the soil. There's an equation, Q equals KH, NFND. Here, K is the hydraulic conductivity, H is the total head loss across the system, NF is the number of flow channels, spaces between flow lines, and N is the number of potential drops, spaces between equipotential lines in the net.
Okay, so you can quantify the flow rate.
Yes. And second, you can determine the water pressure at any point within the soil mass by looking at which equipotential line passes through or near that point. The pressure drop between any two adjacent equipotential lines is the same, HND. Figure 8.7 shows a nice flow net example for seepage under a sheet pile wall.
Now, seeping water isn't just moving. It can also exert forces on the soil particles themselves, can't it?
Yeah.
Cause problems.
Yes, absolutely. As water flows through the soil, it exerts a frictional drag force on the soil particles in the direction of the flow. This is called seepage force. The seepage force per unit volume of soil is equal to the hydraulic gradient, I, times the unit weight of water. So J equals I.
And if that force is acting upwards,
If the flow is upward and the hydraulic gradient is large enough, the upward seepage force can counteract the downward effective weight of the soil particles, their submerged weight. If the upward seepage force becomes equal to the submerged weight of the soil, a critical condition is reached. We call this the quick condition, or sometimes boiling.
boiling. Does the soil actually boil?
No, not like boiling water. It's just a term used because the soil can appear agitated, almost like it's bubbling or boiling, especially in sands. What's actually happening is that the effective stress in the soil becomes zero.
Effective stress goes to zero.
Right. Since shear strength depends on effective stress, toughness plus temperature, the soil loses all its shear strength and can behave almost like a dense liquid. It can't support any load. This happens when the upward hydraulic gradient reaches a certain value called the critical hydraulic gradient, PARC.
How is ERDI calculated?
The critical hydraulic gradient is calculated as the buoyant unit weight of the soil divided by the unit weight of water, so arcable. Or, in terms of specific gravity and void ratio, RC is GS1, 1 plus E.
And this quick condition is obviously bad if you're trying to excavate or build something.
Very bad. It can lead to the failure of excavation bottoms or the instability of dam toes. You might see it happening near sheet pile walls or at the base of cuts where groundwater is seeping upwards under pressure.
So how do we prevent these kinds of problems associated with seepage, like erosion or this quick condition?
One very important technique is to use filters. These are layers of specially selected granular material or sometimes engineered fabrics called geotextiles, placed strategically.
Where are they placed?
Typically, they're placed between the soil that needs protection and the area where water is seeping out, or between different layers of soil in an embankment or dam.
And what do they do?
Filters serve two main purposes. First, the pores in the filter material must be small enough to prevent the fine particles of the protected soil from being washed away or eroded by the seeping water. This prevents internal erosion or piping. Second, the filter material itself must be much more permeable than the soil it's protecting, so that the water can flow through it easily without building up excessive pore water pressure behind or within the filter.
So fine enough to hold soil, coarse enough to let water through easily.
Exactly. There are specific design criteria, often based on the particle size distributions of the filter material and the soil being protected, to ensure these conditions are met. Section 9.6 and equations like 9.18 cover some of these filter design rules. Properly designed filters also increase the factor of safety against heave or boiling by allowing pressure relief.
Okay, that makes sense. We've talked about the pressure of water within the soil, pore water pressure. Now let's zoom out a bit and think about the overall stresses acting within the ground itself, even before we build anything.
Right. Understanding the stresses in the ground, what we call in situ stresses, is absolutely fundamental to analyzing how soil will behave under any kind of load, whether it's from its own weight or from a structure we place on it. We generally need to consider 3 key types of stress at any point within the soil mass.
3 types.
Yes. First, there's the total stress, usually denoted by sigma. This is simply the total weight of everything, soil particles, water, anything above a certain point divided by the area at that point. It's like the total pressure you'd feel at that depth. Second, there's the pore water pressure. This is the pressure exerted by the water filling the void spaces between the soil particles. Below the water table, it's usually hydrostatic pressure.
Okay, total stress and poured water pressure. What's the third?
The third, and arguably the most important for soil behavior, is the effective stress, usually denoted sigma prime. This represents the stress that is actually carried by the solid skeleton of the soil particles through their points of contact.
And how does it relate to the other 2?
This is where the principle of effective stress comes in, one of the most important concepts in all of soil mechanics, developed by Terzaghi. It states that the effective stress is equal to the total stress minus the pore water pressure.
Why is this effective stress so important?
Because it's the effective stress, not the total stress, that largely controls the strength and deformation behavior of soils. Things like shear strength and compressibility are primarily functions of the effective stress. Changes in effective stress cause soil to compress or shear.
Got it. So if we have, say, layers of different soils and maybe a groundwater table somewhere in there, how do we actually figure out these stresses, total, pore water, and effective at different depths?
It's a calculation you do layer by layer, working downwards from the ground surface. To calculate the total vertical stress at a certain depth, you sum up the weights of all the soil layers above that point. You need to know the unit weight of each layer. If a layer is above the water table and unsaturated, you use its moist or bulk unit weight. If it's below the water table, you use its saturated unit weight, thus it.
Okay, so sum of unit weight layer thickness gives total stress.
Exactly. Then, to find the pore water pressure at that depth, you calculate the hydrostatic pressure based on the depth below the free water table. So U equal to where U out, where is the height of water above the point. Above the water table, pore pressure might be 0, or it could be negative due to capillary action.
And then effective stress is just total stress minus pore water pressure.
That's right. Figure 9.99 and the example problems in Chapter 9 walk through these calculations very clearly for different scenarios, like layered soils with the water table at different positions.
You mentioned capillary action possibly causing negative pore pressure above the water table. How does that work, and how does it affect the stresses?
Right, capillary rise. Because of surface tension in the water acting within the tiny pore spaces in the soil, water can actually rise above the level of the free groundwater table, much like water rises in a thin straw.
The capillary fringe.
Exactly, the capillary fringe. In this zone, the soil might be fully or partially saturated, but the water in the pores is actually under tension. It has a pressure less than atmospheric pressure. We call this negative pore water pressure, or suction.
And negative pore pressure means?
Well, if the LRU is negative in our effective stress equation, then subtracting a negative number means the effective stress actually increases. So, capillary suction pulls the soil grains together and increases the effective stress in the capillary zone.
How high can this capillary rise be?
The height to which water will rise depends inversely on the size of the pores in the soil. Smaller pores mean higher capillary rise. Equation 9.23 relates it to surface tension and pore radius. Hazen's empirical formula, equation 9.24, gives a rough estimate based on the effective grain size, D10, and void ratio. Table 9.2 gives typical ranges that can be negligible in coarse gravel, maybe a few centimeters or inches in sand, but potentially several meters in fine silts and clays. Figure 9.15 illustrates this.
Interesting. Okay, so that covers the stresses already existing in the ground. Now, what happens to those stresses when we put a new load on the surface, like when we build a foundation for a building?
When you apply an external load to the ground surface, it causes an increase in stress within the soil mass below that load. The soil has to distribute that load downwards and
It
outward.
doesn't just go straight down.
No, it spreads out. How that added stress is distributed depends on several factors, including the size and shape of the loaded area and the assumed properties of the soil, often assumed to be elastic, homogeneous, and isotropic for simpler calculations.
And we have ways to estimate this stress increase.
Yes, we have various theories and solutions, mostly based on the theory of elasticity, to estimate this stress increase at different points beneath different types of loads. For example, Brusinisk's theory gives the stress increase under a concentrated point load, figure 10.4. There are solutions for loads applied along a line, like from a long wall footing, figure 10.6, loads over a uniformly loaded strip, like a continuous footing, figure 10.9, and loads over rectangular or circular areas, figure 10.12.
So formulas and charts for different load shapes.
Exactly. These solutions typically give the increase in vertical stress, but also horizontal and shear stresses if needed. For more complex or irregularly shaped loaded areas, engineers might use influence charts, like the famous Newmark's chart, figure 10.29, which provides a graphical way to determine the increase in vertical stress at a specific point beneath the loaded area.
Okay, so we put a load on the soil, the stress inside the soil increases, and then the soil compresses under that increased stress, which leads to settlement of the structure on top. Let's dive into this idea of soil compressibility and settlement.
Right. Soil compressibility is the tendency of a soil mass to decrease in volume when it's subjected to increased pressure or loading. The resulting vertical downward movement of the ground surface or foundation is what we call settlement.
And settlement isn't just one single thing, is it?
No, we generally break down the total settlement of a foundation into three main components, which happen over different timescales. First, there's elastic settlement or immediate settlement. This happens relatively quickly, almost as the load is applied. It's due to the elastic deformation of the soil particles and the soil mass without any change in water content. Second, and often the most significant component for foundations on clay, is primary consolidation settlement. This is a time-dependent process that occurs in saturated cohesive soils like clays and silts, as water is gradually squeezed out of the pores under the increased load.
Water squeezing out over time.
Exactly. And third, there's secondary compression, sometimes called creep. This is a very slow, long-term compression of the soil that occurs after the primary consolidation is essentially complete, under constant effective stress. It's due to the gradual rearrangement of soil particles and the compression of the soil structure itself.
Let's focus on that primary consolidation settlement in clays. You said it's due to water squeezing out. What's the underlying mechanism that causes that?
Okay. Primary consolidation in saturated clays happens because when you first apply a load to the foundation, the soil skeleton can't immediately adjust because the water trapped in the tiny pores can't escape instantly. Water is practically incompressible compared to the soil structure. So initially, the entire increase in total stress from the load is carried by the pore water, resulting in an increase in pore water pressure above the initial hydrostatic pressure. We call this excess pore water pressure, figure 11.6b.
So the water takes the initial hit.
Yes. Now, because the clay has low permeability, this excess pore water pressure can only dissipate slowly as the water gradually flows out of the clay layer towards a more permeable drainage layer, like sand above or below. As the water leaves, the excess pore water pressure decreases, and the load is gradually transferred from the water to the soil skeleton. This causes an increase in the effective stress acting on the soil particles.
An increased effective stress causes compression.
Precisely. This increase in effective stress causes the soil skeleton to compress, the void ratio decreases, and the ground surface settles. This process continues until all the excess pore water pressure has dissipated. The effective stress has increased by the full amount of the applied load stress, and primary consolidation is complete.
And I understand the history of how much load a clay has experienced in the past plays a really big role in how much it compresses now, right? This idea of normally versus over-consolidated clays.
Absolutely crucial distinction. Normally consolidated NC clay is one that is currently experiencing the maximum effective vertical stress that it has ever been subjected to in its geological history. It's kind of at its peak past pressure right now. An over-consolidated OC, on the other hand, has been subjected to a higher effective stress at some point in the past than its current effective overburden stress. This past maximum effective stress is called the pre-consolidation pressure.
So C keys is greater than the current sol for an OC clay.
Exactly. This past higher pressure could have been due to the weight of overlying soil or glaciers that have since eroded away, or maybe due to desiccation, drying.
But how do we quantify how overconsolidated it is?
We use the overconsolidation ratio, OCR. It's defined as the ratio of the preconsolidation pressure to the current effective overburden stress. OCR equals SICAR. For a normally consolidated clay, OCR equals 1. For an overconsolidated clay, OCR 1. The higher the OCR, the more heavily overconsolidated the clay is.
How do engineers figure out this pre-consolidation pressure ski?
Usually from a laboratory test called a consolidation test or odometer test. In this test, a sample of clay is subjected to increments of vertical load, and its compression is measured over time. From the results, you plot the void ratio against the logarithm of the effective stress. The resulting curve typically shows a distinct bend or knee. There's a graphical procedure developed by Casagrande, shown in figure 11.8, that helps estimate this from the shape of this Elog's curve. There are also some empirical equations that try to estimate CUS based on other soil properties, but the lab test is more direct.
Okay. And how do we actually measure or predict how much a clay will compress under a given load increase? Is that where the compression index comes in?
Yes. For calculating consolidation settlement, we use indices derived from that Elog's curve from the consolidation test. The compression index, CC, is a measure of the compressibility of a normally consolidated clay. It's defined as the slope of the straight line portion of the Elog's curve in the range where the effective stress is greater than the pre-consolidation pressure. This is often called the virgin compression line.
So steeper slope means more compressible.
Yes, a higher CC means the void ratio decreases more for a given increase in the log of effective stress, so the soil is more compressible. Skempton, back in 1944, proposed an empirical correlation to estimate CC based on the liquid limit, LL for normally consolidated clays. CC at 0.009 LL10, where LL is in percent, equation 11.35. There are other correlations too, like Rendon-Herrero's equation 11.36 and others shown in table 11.6.
Okay, that's for normally consolidated clays or when you load an OC clay past its... What about reloading or unloading an overconsolidated clay below its pre-consolidation pressure?
Right. When you load or unload an overconsolidated clay within the stress range below its suck, the compressibility is much lower. The slope of the Elog's curve in this recompression or swelling range is called the swell index or recompression index, CFIS, sometimes CR.
So CS is generally smaller than CC.
Much smaller, typically about 15th to 110th of CC. This means OC clays compress much less than NC clays for the same stress increase, as long as the final stress doesn't exceed the cells. There are also empirical relationships to estimate Cs, like Nagaraj and Murty's equation 11.41, and table 11.7 gives some typical values.
So using these indices, CC and Cs, engineers can calculate the total amount of primary consolidation settlement that will eventually occur under a given load.
Yes, using formulas that incorporate the initial void ratio, the change in effective stress, and the appropriate index, CC or Cs or both, if the load crosses B.
But what about how long that settlement will take? Years, decades. That seems pretty important for construction. That's where Terzagh's consolidation theory comes in.
Exactly. Terzagh's one-dimensional consolidation theory, developed way back in the 1920s, provides the framework for predicting the time rate of consolidation settlement. It tells us not just how much settlement will occur, but how long it will take.
And what's the basis of the theory?
It's based on a few key assumptions. The clay layer is homogeneous and fully saturated, compression and water flow are one-dimensional, vertical, Darcy's law is valid, and the soil properties, like permeability K and compressibility MV, remain constant during consolidation. The theory leads to a differential equation that describes how the excess pore water pressure dissipates over time and depth within the clay layer.
So it models the water escaping.
Yes. The solution to this equation depends on a property called the coefficient of consolidation, CV. This parameter combines the soil's permeability and compressibility, CVHK, MVM, and basically governs how quickly consolidation occurs. A higher CV means faster consolidation. The theory uses a dimensionless time factor, THCV, THDR, where T is time and HDR is the length of the longest drainage path for the water escaping the clay layer.
Drainage path, distance to sand.
Right, distance to the nearest permeable layer, sand or gravel, where the water can freely escape. If the clay is sandwiched between two sand layers, HDR is half the clay layer thickness. If it's on impermeable rock with sand only above, HDR is the full thickness.
And this time factor T relates to how much settlement has happened.
Yes, the degree of consolidation, U, which is the percentage of the total primary settlement that has occurred at time T, is directly related to the time factor T. There are charts and equations that give U as a function of T. So if you know CV and the drainage path HDR, you can predict the settlement at any time T.
Sometimes construction needs to happen faster than natural consolidation allows, right?
Oh, yeah.
Can we speed it up?
Yes, absolutely. Especially for thick layers of soft clay where consolidation might take many years, engineers often use techniques to accelerate the process. The most common method is installing vertical drains.
Vertical drains, like straws in the clay.
Kind of. They used to use sand drains, but now more commonly they use prefabricated vertical drains, or PVDs, sometimes called wick drains. These are typically plastic strips with channels that are installed vertically through the clay layer at regular intervals. Figure 11.38 shows this.
And what do?
They drastically shorten the drainage path for the escaping pore water. Instead of having to flow all the way vertically to a sand layer, the water only needs to flow a short distance horizontally to the nearest PVD, and then it can travel quickly up or down the drain. This dramatically reduces the time required to achieve primary consolidation, maybe from years down to months.
Very clever. Okay, we've looked at how soil compresses under load. Now, what about its strength? Its ability to resist failure. That's got to be crucial for things like making sure slopes don't collapse and that foundations can actually support the buildings on top of them without the ground giving way.
Absolutely. The sheer strength of soil is its ability to resist failure and sliding along an internal surface when subjected to shear stresses. It's a fundamental property that governs the stability of slopes, the ultimate bearing capacity of foundations, and the pressure that soil exerts on retaining structures. Without sufficient shear strength, the ground fails.
And what gives soil this sheer strength? Where does it come from?
Shear strength in soils primarily comes from two components: cohesion and friction.
Cohesion and friction, like glue and sandpaper.
That's a decent analogy, actually. Cohesion represents the inherent shear strength that the soil possesses, even when there's no normal stress pressing the particles together. It's often related to electrochemical bonds between clay particles or weak cementation. Friction represents the resistance to sliding between the soil particles, which is dependent on the normal stress pressing them together. Higher normal stress means higher frictional resistance.
And the Moore-Coulomb failure criterion is the rule that describes how these things relate to predict failure, right?
Yes, exactly. The Moore-Coulomb failure criterion is the most widely used model for shear strength in soils. When expressed in terms of effective stress, which is what generally controls strength, the equation is TACE plus C plus tan. That's equation 12.2.
TACE plus tan. Let's break that down.
Okay. Hef is the shear strength, or the maximum shear stress the soil can withstand on a particular plane before failing. Hess is the effective normal stress acting perpendicular to that same plane. Hess is the effective cohesion intercept, and Hef A prime is the effective angle of internal friction.
So the strength depends on cohesion plus a frictional component that increases with effective normal stress.
Precisely. The TANS term represents how much the frictional resistance increases for a given increase in effective normal stress. Table 12.1 in the reference gives typical ranges for the drained angle of friction for different types of sands and silts. For loose sand, it might be around 28-30 degrees, while for dense sand, it could be over 40 degrees. Cohesion is often assumed to be 0 for uncemented sands and gravels, but it can be significant for clays.
How do engineers actually measure these shear strength parameters, C and C, for a specific soil? What tests do they run?
We use different types of laboratory shear strength tests, primarily the direct shear test and the triaxial compression test.
Direct shear test.
The direct shear test is relatively simple. A soil sample is placed in a box that's split horizontally into two halves. A constant normal force is applied vertically, and then a shear force is applied horizontally to one half of the box, forcing the soil to shear along the predetermined horizontal plane between the two halves. You measure the shear force needed to cause failure at different normal stresses.
And you can control drainage.
Yes, you can run these tests either drained, where you shear slowly enough that any excess pore water pressure can dissipate, giving you effective strength parameter C and SID, or undrained, where you shear quickly so water can't escape, giving undrained strength parameters, particularly relevant for short-term analysis in clays.
Okay. And the triaxial test sounds more complex.
It is more sophisticated and generally considered more reliable because you have better control over stresses and drainage, and failure isn't forced along a specific plane. In a triaxial test, figure 12.19 shows the setup. A cylindrical soil sample is enclosed in a rubber membrane and placed inside a pressure chamber. First, an all-around confining pressure, the chamber pressure, is applied to the sample. Then, an additional axial stress, the deviator stress, is applied vertically through a piston until the sample fails in shear, usually along an inclined plane.
And again, you can control drainage.
Yes, that's a key advantage. You can run different types of triaxial tests depending on the drainage conditions during the confining stage, consolidation, and the shearing stage. The main types are consolidated drained CD test, where the sample is allowed to consolidate under CS3 and then sheared slowly enough for full drainage, gives CS3. Consolidated undrained CU test, where it consolidates under 3, but then sheared quickly without drainage, measures pore pressure changes, also gives CSI directly. And unconsolidated undrained U test, where no consolidation or drainage is allowed at any stage, gives undrained shear strength, SU or Q, and FU-ISI, often used for short-term stability of clays.
So different tests for different field situations and timeframes.
Exactly. The choice of test depends on what engineering problem you're trying to solve and whether you're interested in a long-term drained or short-term undrained behavior.
Now, I remember reading something about peak shear strength versus residual shear strength, especially when it comes to clays. What's that about?
Yes, that's an important concept, particularly for over-consolidated clays or dense sands when sheared in a drain test. These soils often exhibit a peak shear strength at relatively small strains, but as the shearing continues and the strain increases, the strength can decrease significantly to a lower constant value called the residual shear strength. Figure 12.2 illustrates this.
Why does the strength drop?
It's often due to the particles rearranging. In clays, the plate-like particles tend to become oriented parallel to the direction of shear along the failure surface as large displacements occur. This more ordered arrangement offers less resistance to sliding. In dense sands, dilation volume increase during initial shearing contributes to peak strength, but this effect diminishes at larger strains.
And this residual strength matters for...
It's particularly important for analyzing the stability of slopes where previous landslides have occurred, or where large deformations might happen. The long-term stability might be governed by the lower residual strength, not the initial peak strength. Figure 12.11 shows how the residual shear strength relates to effective normal stress, defining a residual friction angle, which is often related to the amount of clay-sized particles in the soil.
Okay, so soil has strength to resist shearing. Now, if we build something like a retaining wall to hold back soil, that soil behind the wall is going to push against it horizontally. Let's talk about lateral earth pressure.
Right. Lateral earth pressure is the pressure that soil exerts in the horizontal direction perpendicular to a vertical plane. It's a really critical consideration in the design of retaining walls, basement walls, braced excavations, sheet pile walls, tunnels, anything that holds back earth.
And it's not just one value, is it? There are different conditions.
Yeah. Correct. We usually consider 3 main conditions or states of lateral earth pressure. First, there's the at-rest condition. This is the lateral pressure the soil exerts when the retaining structure is completely rigid and doesn't move at all horizontally. We quantify this using the coefficient of earth pressure at rest, CO. CO is the ratio of the horizontal effective stress to the vertical effective stress when there's no lateral strain. CO-COS.
How do we know CUF?
It depends on the soil type and its stress history. For normally consolidated soils, there's a well-known empirical formula proposed by Jackie, 1944. CO and 1 sin. Equation 13.5. For over-consolidated soils, CO is higher and also depends on the OCR.
Okay, that's at rest. What happens if the wall moves?
If the wall moves away from the soil backfill, even a small amount, the horizontal stress decreases. If the wall moves sufficiently far, the soil reaches a state of plastic equilibrium and the horizontal stress reaches a minimum value. This is called the active earth pressure condition. We use the coefficient of active earth pressure, CUS, for actual, with the active pressure, CUS.
So active pressure is the minimum push from the soil.
Yes. Conversely, if the wall is pushed into the soil backfill, the horizontal stress increases significantly. Again, if there's enough movement, the soil reaches a different state of plastic equilibrium, mobilizing its maximum possible lateral resistance. This is the passive earth pressure condition. The passive pressure PP equals QUAV, where Kpop is the coefficient of passive earth pressure.
And passive pressure is the maximum resistance the soil offers.
That's right. Passive resistance is much higher than active pressure. Kpop is much larger than Ka.
How do we calculate these coefficients? Ka and Ka.
There are a couple of classical theories. Rankine's theory, developed in the 1850s, provides a relatively simple way to calculate Ka and Kpop for the specific case of a vertical wall with no friction between the wall and the soil and a horizontal backfill surface. For this case, cop half 45 degrees A2, equation 13.3, and cop equals tant 45 degrees plus 2, equation 13.6. Notice that cop is the reciprocal of Ka. The pressure distribution is assumed to be triangular, increasing linearly with depth. Figures 13.2 and 13.3 show the active and passive cases.
Rankine's theory sounds a bit simplified. What if there is wall friction or the backfill isn't level?
Good point. For more general cases, including wall friction, angle at, and inclined backfill, angle but, we often use Coulomb's theory, developed even earlier in the 1770s. Coulomb's theory uses a wedge analysis, considering the equilibrium of a potential sliding wedge of soil behind the wall. It gives more complex formulas for Ka and Kop that account for a phi, the wall inclination angle, and the backfill slope angle. Figure 13.41 shows the forces involved in Coulomb's active case. Coulomb generally gives slightly different, often higher active pressures than Rankine when wall friction is included.
And what about other factors like extra loads on top of the backfill or groundwater?
Those definitely need to be considered. If there's a surcharge load, like from traffic or stored materials, on the backfill surface, it adds a uniform horizontal pressure to the active or passive pressure distribution. Equations 13.1 and 13.15 illustrate this. If the groundwater table is within the backfill, figure 13.5, you need to calculate the earth pressure using effective stresses, using buoyant unit weight below the water table, and then add separate hydrostatic pressure from the water itself. This significantly increases the total pressure on the wall.
What about earthquakes? Does the pressure change then?
Yes, dramatically. During an earthquake, the ground shaking induces additional dynamic forces on the soil wedge behind the wall, which increases the active pressure and decreases the available passive resistance. The Mononobe-Okabe theory, developed in the 1920s, is a common method used to estimate these seismic earth pressures. It's essentially a modification of Coulomb's wedge theory that includes horizontal and vertical inertia forces due to the earthquake acceleration. It results in modified dynamic active K and passive K earth pressure coefficients, equations 13.93, 13.94, and 13.95, that depend on the earthquake acceleration coefficients.
So seismic design is crucial for retaining walls in earthquake zones.
Absolutely. The dynamic increment can be substantial.
You mentioned different types of retaining walls earlier. What are the common ones?
Broadly, we can think of rigid retaining walls and mechanically stabilized earth, MSE walls. Rigid walls include gravity walls, which rely primarily on their own massive weight for stability, often made of concrete or stonemasonry. Cantilever walls are typically L-shaped or T-shaped reinforced concrete walls that use the weight of the soil on the heel of the footing to help resist overturning. Counterfort walls are similar to cantilever walls but have vertical bracing ribs, counterforts, connecting the wall stem and the base slab to handle larger heights. MSE walls, discussed in section 13.14, are quite different. They consist of a facing, often precast concrete panels or modular blocks, combined with layers of soil reinforcement, like metal strips or geosynthetic grids, extending back into the soil fill. The reinforcement creates a stable composite soil mass that retains the earth behind it. They become very popular.
Okay, lots of options depending on the situation. Now, what if we're not building a wall, but we have a natural slope? Or maybe we've created one by digging a cut slope or building an embankment to fill slope. How do we figure out if that slope is going to be stable or if it might fail in a landslide?
Slope stability analysis is a huge part of geotechnical engineering. It's all about determining the factor of safety of a natural or man-made soil slope against failure by sliding or collapsing.
And slope failures can happen in different ways.
Yes, there are various types of slope failures or movements. We can see falls, where rock or soil detaches and drops rapidly, topples, where a mass rotates forward, slides, which are probably the most common type analyzed, where a mass of soil or rock moves downslope along a distinct surface or zone of weakness. These slides can be rotational, with a curved failure surface, often in cohesive soils, or translational, with a planar failure surface, often controlled by a weak layer or joint. And then there are flows, where the soil moves like a viscous fluid, like debris flows or mud flows. Figures 15.4, 15.5, and 15.6 illustrate some of these.
So how do we analyze the stability, especially for those slides?
The approach depends on the geometry of the slope and the potential failure mechanism. For what we call infinite slopes, where the slope is very long compared to the depth of the potential failure surface, and the conditions are fairly uniform, we can use relatively simple limit equilibrium equations. We analyze the forces acting on a single vertical slice of soil parallel to the slope.
Infinite slopes, like a long, uniform hillside.
Kind of, yes. Or the surface layer of a very wide embankment. For cohesionless soils like dry sand, the factor of safety, Fs, simply depends on the slope angle and the soil's friction angle, Fs in equation 15.9. If there's seepage parallel to the slope, the Fs is reduced, equation 15.13. For cohesive soils under drained conditions, cohesion also contributes to stability, equation 15.13.
Okay, that's for infinite slopes. What about more typical finite slopes, like an embankment or a cut slope where the failure surface might be curved?
Right. For finite slopes, the potential failure surface is often assumed to be curved, frequently approximated as a circular arc for rotational slides, especially in cohesive soils. Analyzing these requires more complex methods, most commonly the method of slices.
Method of slices. What's that?
The idea is to divide the potential sliding mass of soil above an assumed circular failure surface into a number of vertical slices. Then you analyze the forces acting on each individual slice its weight, the normal and shear forces on its base along the failure arc, and the forces acting between adjacent slices, figure 15.29b. By summing forces and moments for all the slices and comparing the total resisting forces, or moments, along the failure arc to the total driving forces, or moments causing instability, you can calculate the factor of safety for that specific potential failure circle. Equation 15.37 gives a general form.
Sounds complicated, especially with the forces between slices.
It can be. The simplest version, called the ordinary method of slices, or Frobenius method, makes simplifying assumptions and ignores the interslice forces, which isn't entirely accurate but is easy to calculate. Bishop's simplified method, figure 15.32, is a more refined and commonly used approach. It satisfies vertical force equilibrium for each slice and overall moment equilibrium, making some simplifying assumptions about the interslice forces. It generally gives more accurate factors of safety than the ordinary method. Equation 15.59 provides the formula for Fs in Bishop's method.
So Bishop's method is better.
Generally, yes, for circular failure surfaces. There are even more rigorous methods, like Spencer's solution, figure 15.35, that satisfy all conditions of static equilibrium, both force and moment equilibrium, and make more reasonable assumptions about interslice forces. These usually require computer programs to solve.
What about analyzing clay slopes, especially under undrained conditions like right after construction?
For the short term, undrained stability analysis of slopes in saturated clay, where SUA0 in strength is defined by the undrained shear strength, SU or KU, engineers often use stability charts based on a stability number originally developed by Taylor. This number relates the critical height of the slope, the unit weight of the soil, the undrained strength, and the slope angle. Figure 15.13 provides such a chart.
And how does groundwater affect slope stability in general?
The presence of groundwater and poor water pressure within a slope significantly reduces its stability. Remember, shear strength depends on effective stress. Positive poor water pressure reduces the effective normal stress on the potential failure surface, which in turn reduces the frictional resistance component of shear strength.
So more water pressure means lower factor of safety.
Definitely. In stability analyses using methods like Bishop's, the pore water pressure is often accounted for using a pore pressure ratio parameter, ρ, which relates the pore pressure to the weight of the soil above that point, equation 15.61. Tables like 15.3 relate ρ values to factors of safety. High pore pressures are a major cause of landslides.
Are there specific situations that are particularly critical for embankments?
Yes. A couple of key scenarios often analyzed are stability during rapid drawdown of the water level against an embankment, like in a reservoir, where the external supporting water pressure is removed quickly, but the pore pressures inside the embankment don't have time to adjust, reducing stability. Also, the stability at the end of construction for embankments built of cohesive fill is critical, as pore pressures might build up during compaction and haven't dissipated yet. Fetzer 15.45 illustrates the rapid drawdown case.
Okay, slope stability is clearly complex. Now let's move down from the slope to the flat ground where we build foundations. How do we make sure the soil underneath a shallow foundation, like a footing for a column or wall, can actually support the load from the structure without the ground failing underneath it?
That brings us to the concept of bearing capacity of shallow foundations. Bearing capacity is essentially the ability of the soil layer just beneath a foundation to safely carry the load transmitted by the foundation without undergoing shear failure or causing excessive settlement.
Shear failure of the soil under the foundation.
Yes. If the load applied by the foundation is too high, it can cause the soil beneath and adjacent to the footing to fail and shear, leading to large, sudden settlement or tilting of the foundation.
And this failure can happen in different ways.
Right. Depending on the soil type, especially its density and stiffness, and the depth and shape of the foundation, we generally recognize three main modes of bearing capacity failure, as observed by Vesic and shown in Figure 16.9. General shear failure is a sudden, catastrophic failure, typical in dense sands or stiff clays, involving a well-defined failure surface extending from the footing edge up to the ground surface, often accompanied by bulging of the ground surface nearby. Local shear failure is more common in medium-dense sands or medium-stiff clays. The failure surfaces are less defined, there's significant settlement before failure becomes obvious, and the bulging might be slight. Punching shear failure occurs in loose sands or soft clays, or when the foundation is deep relative to its width. The soil directly beneath the footing compresses significantly, and the failure surfaces don't extend very far laterally. There's large settlement with minimal bulging.
So the soil type really matters. How do we calculate the ultimate load the soil can take before failure? Terzaghi, who we've mentioned a lot, developed a key equation for this, didn't he?
Yes, Terzaghi's bearing capacity equation, developed in 1943, is still a cornerstone of foundation design, especially for a conceptual understanding. His equation calculates the ultimate bearing capacity, Q, the maximum pressure the soil can withstand before general shear failure occurs for a long strip footing. The equation is QU equals CNC plus QNQ plus 0.5 BNU, equation 16.31.
Okay, let's unpack that. QU, CNC plus QNQ plus 0.5 BNO. What are the terms?
Okay. Q is the ultimate bearing capacity. C is the effective cohesion of the soil beneath the footing. Q is the effective overburden pressure at the foundation level. Essentially, the weight of the soil beside the footing. Q is the width of the footing. With BO, this is the depth of the footing. B equals the effective unit weight of the soil beneath the footing. B is the width of the footing.
And NC and Q.
Those are the bearing capacity factors. They are dimensionless factors that depend only on the soil's effective angle of internal friction. NC relates to the contribution of cohesion, NQ relates to the contribution of the surcharge, and NO relates to the contribution of the soil's weight beneath the footing. Terzaghi derived theoretical values for these factors, and they increase significantly as phi increases. Table 16.3 provides these values.
So the equation combines effects of cohesion, overburden pressure, and soil weight.
Exactly. It captures the main sources of resistance. However, Terzaghi's original equation was for a strip footing experiencing general shear failure. Engineers have since developed modifications to account for other footing shapes, like square, circular, rectangular, and for the depth of the footing below the ground surface. These usually involve multiplying the terms in Terzaghi's equation by shape factors, Fs, and depth factors, Fd.
What about bearing capacity in clays, especially under undrained conditions, like soon after loading?
Right. For saturated clays under undrained conditions, short-term loading, the analysis is often simplified by assuming C equals 0. In this case, the bearing capacity factors NU becomes 1 and NOS becomes 0. The equation simplifies, and the ultimate bearing capacity depends primarily on the undrained shear strength, Q, or SU, and the factor NC Skempton, 1951, proposed values for NC specifically for undrained analysis that depend on the shape and depth of the foundation. For a strip footing at the surface, NC is 5.14, but it increases with depth and differs for square or circular footings. Figure 16.0 shows Skempton's NC factors.
So Q for clays is roughly proportional to the undrained shear strength, Q.
Essentially, yes. QN/NC plus CO.
Now, Q is the ultimate failure load. Engineers don't design for that, right? They use an allowable load.
Absolutely. We never design a foundation to be right at the point of failure. We always apply a factor of safety, FS. The allowable bearing capacity, qual, is the ultimate bearing capacity, Q, divided by a suitable factor of safety. Qual equation 16.43.
What's a typical factor of safety?
FS is usually between 2.5 and 4, commonly around 3, depending on the importance of the structure, the reliability of the soil parameters, and the potential consequences of failure.
So qual is the maximum pressure the foundation is allowed to apply to the soil.
Yes, based on shear strength failure. However, there's another crucial consideration, settlement.
Ah, right. The foundation might not fail in shear, but it could still settle too much.
Exactly. In many cases, especially for foundations on sands or even for wider foundations on clays, the allowable bearing capacity might actually be governed by the need to limit the total settlement or differential settlement, uneven settlement between different parts of the structure, to tolerable levels for the structure.
Right.
So engineers calculate the ultimate bearing capacity, Q, apply a factor of safety to get qual strength, but then they also estimate the settlement that would occur under various pressures and determine the pressure coefficient that corresponds to the maximum acceptable settlement. The final allowable bearing pressure used for design is the lower of these two values. Section 16.9 discusses settlement considerations.
So strength and settlement both need checking. Are there any quick ways to estimate allowable bearing pressure, maybe from field tests?
Yes, particularly for foundations on sandy soils. There are empirical correlations that relate the results of in situ tests, like the standard penetration test, SPT, directly to the allowable bearing pressure, often incorporating a settlement criterion, like limiting settlement to 1 inch or 25 millimeter. Equations like 16.47 provides such correlations based on the corrected SPT-N value. These are very commonly used in practice for preliminary design or smaller projects, but they are empirical.
Okay, a lot goes into ensuring a foundation is safe. We've covered a huge amount about natural and engineered soil used for construction. But what about when we're trying to contain things like waste in landfills? Geotechnical engineering plays a crucial role there too, doesn't it, in preventing pollution?
Absolutely. Landfill design and containment systems are a major application of geotechnical principles, specifically focused on preventing harmful liquids called leachate from escaping the landfill and contaminating the surrounding soil and groundwater.
Leachate, the nasty stuff that drains through the waste.
Exactly. It can contain all sorts of contaminants. So modern landfills rely heavily on engineered liner systems at the bottom and sides and cover systems at the top to contain this leachate and manage landfill gas.
And clay is often a key part of these liners.
Yes, compacted clay liners, CCLs, have traditionally been a fundamental component. The goal is to create a layer of clay with very low hydraulic conductivity, permeability, to minimize the amount of leachate that can seep through.
How low does the permeability need to be?
Regulatory requirements typically demand that the compacted clay liner achieve a hydraulic conductivity K of less than or equal to 1 by 10 to 7 centimeters per second. That's very impermeable. Figure 17.3 illustrates a typical liner profile, including a CCL.
And achieving that low permeability requires careful construction.
Extremely careful. It depends heavily on selecting the right type of clay, controlling the moisture content during compaction, usually slightly wet of the optimum moisture content determined by the Proctor test, and achieving a high degree of compaction with appropriate equipment to minimize voids and clod sizes. There are specific, like those developed by Daniel and Benson in 1990, that outline best practices for constructing effective CCLs.
But clay isn't the only material used, right? You mentioned engineered materials earlier, geosynthetics. Are they used in landfill liners too?
Yes, very much so. Geosynthetics are now essential components in modern landfill liner and cover systems, often used in combination with compacted clay or as alternatives in some cases.
Geosynthetics.
Yeah.
What exactly are they?
Geosynthetics are planar products manufactured from polymeric materials, specifically designed for use in geotechnical and geoenvironmental engineering applications. There's a whole family of them.
What are the main types?
The main types include geotextiles, which are permeable fabrics looking somewhat like felt or woven cloth; geomembranes, which are essentially impermeable plastic sheets or liners; geogrids, which are net-like or grid structures used mainly for reinforcement; geonets, which are also grid-like but designed specifically for drainage; and geocomposites, which are combinations of two or more geosynthetics, like a geonet bonded to geotextiles on both sides to create a drainage layer that also filters.
And they serve different functions in a landfill.
Yes, geosynthetics perform several major functions, sometimes more than one at once. Separation, preventing mixing of different soil layers; reinforcement, adding tensile strength to soil; filtration, allowing water to pass while retaining soil particles; drainage, collecting and conveying liquids or gases; and acting as a moisture barrier, containing liquids.
So which ones are most common in liners?
In landfill liners, geomembranes are critical. They provide the primary barrier to leachate migration due to their very low permeability. High-density polyethylene is a common type. Geotextiles, figure 17.4 shows some examples, are often used as protective layers above and below the geomembrane to prevent puncture, and also as filters in drainage layers. Geonets or geocomposites are used to create leachate collection and removal systems, LCRS, above the primary liner, and leak detection systems, LDS, between liners.
Between liners, so they use multiple layers.
Yes, modern regulations, especially for hazardous waste landfills, often require double liner systems. A typical double liner system, figures 17.10 and 17.1 on show examples, might consist of, from bottom up, a compacted clay layer, a primary geomembrane, a leachate collection system, geonet, geotextile, a secondary geomembrane, the primary liner, and another leachate collection system above that, just below the waste. The layer between the two geomembranes acts as a leak detection zone.
Wow, multiple layers of protection. Seems very thorough.
It needs to be, given the potential environmental consequences of a leak.
Okay, so whether we're building a skyscraper, a road, a dam, or a landfill, it all comes back to the soil. And before we can even start designing any of these things, we absolutely need to know what kind of soil we're actually dealing with at the specific site. That's where subsoil exploration comes in, right? The investigation phase.
Absolutely essential. Subsoil exploration, or site investigation, is the process of determining the nature and sequence of the soil strata, the groundwater, and the relevant physical and mechanical properties of the soil and rock beneath a proposed construction site. Chapter 18 is dedicated to this.
Why is it so crucial? What information are we trying to get?
Well, the purposes are numerous. We need to determine the type, depth, and extent of different soil layers. We need to locate the depth to bedrock if it's relevant. We need to find the groundwater level and understand its potential variations. We need to obtain disturbed and undisturbed soil samples for laboratory testing to determine properties like particle size distribution, Atterberg limits, strength, and compressibility. We might perform in situ tests to measure properties directly in the ground. All this information is vital for selecting the right type of foundation, designing it safely and economically, predicting settlement, evaluating slope stability, designing earthworks, assessing potential construction problems. The list goes on. It's the foundation, literally, of good geotechnical design.
So what are some of the common methods engineers use to actually explore the subsurface? How do they see underground?
There's a range of methods, often used in combination. Direct methods involve physically accessing the subsurface. Test pits, Figure 18.1, are shallow excavations, maybe 3-5 meters deep, that allow direct visual inspection of the soil layers and easy collection of bulk samples. They're great for shallow investigations. For deeper exploration, drilling boreholes is standard practice. There are different drilling techniques depending on the soil type and depth. Auger boring uses a screw-like auger to advance the hole, suitable for cohesive soils and shallow depths. Wash boring uses circulating water to remove cuttings, faster but disturbs the soil more. Rotary drilling uses a rotating drill bit and circulating drilling fluid, like mud, and is suitable for penetrating most soil types and rock. Figure 18.2 shows rotary drilling.
Are there also ways to get information without digging or drilling?
Yes, geophysical methods are indirect techniques that measure some physical property of the subsurface materials, like electrical resistivity, seismic wave velocity, or ground-penetrating radar signals, from the surface or within boreholes. These can help delineate strata boundaries or locate anomalies over larger areas relatively quickly, often complementing the information from boreholes.
Okay, so we drill boreholes. How do engineers get actual samples of the soil from down there to bring back to the lab for testing?
Soil sampling is a critical part of the borehole drilling process. We use different types of samplers depending on whether we need a disturbed or an undisturbed sample. Disturbed samples are collected using devices like the split spoon sampler, Figure 18.6. This is a thick-walled steel tube that's split lengthwise and driven into the soil at the bottom of the borehole, usually as part of the standard penetration test, SPT. While the sequence of layers is preserved, the soil structure itself is significantly disturbed by the driving process. These samples are suitable for visual classification, water content determination, particle size analysis, and Atterberg limits.
And undisturbed samples?
Yeah.
For strength tests?
Exactly. For laboratory tests, where the natural structure and stress state of the soil are important, like consolidation tests or shear strength tests, we need undisturbed samples. These are typically obtained using thin-walled tube samplers, often called Shelby tubes, Figure 18.7. These are seamless steel tubes with a sharp cutting edge that are pushed, not driven, into the soil at the bottom of the borehole. They need to be handled very carefully during extrusion, transport, and storage to minimize disturbance. Getting a truly undisturbed sample, especially in sensitive soils, is challenging but crucial for reliable lab results.
You mentioned the standard penetration test, the SPT, is done with a split spoon sampler. That seems like a really common test done out in the field. What does it tell us?
The SPT is indeed one of the most widely used in situ tests in geotechnical engineering worldwide, especially in North America and Asia. It's relatively simple and economical. The test involves driving that standard split spoon sampler, 2-inch outer diameter, 138-inch inner diameter, into the soil at the bottom of a borehole over a distance of 18 inches, 450 millimeter. The driving is done using a 140-pound, 63.5 kilogram hammer, dropped freely from a height of 30 inches, 760 millimeters. Figure 18.8 shows the setup. The key result is the N value, which is the number of hammer blows required to drive the sampler through the middle, 12 inches, 300 millimeters of the 18-inch drive, i.e. ignoring the first 6 inches of seating drive.
So N is blows per foot. What does a high N value mean?
A higher N value generally indicates denser or stiffer soil. The N value gives engineers a good qualitative indication of the soil's consistency for clays or relative density for sands. More importantly, there are numerous empirical correlations that relate the SPT N value to various important soil properties. For sands, N values are correlated with relative density and the angle of internal friction. For clays, they're correlated with undrained shear strength or unconfined compressive strength, Q, equation 18.8 and table 18.4 give examples. These correlations are widely used in practice for preliminary design.
But I've heard the measured N value needs to be corrected.
Yes, that's very important. The raw field N value can be affected by several factors, including the pressure of the soil above the test depth, overburden pressure, and significantly, the actual amount of energy delivered to the drill rods by the hammer system, which can vary depending on the hammer type, release mechanism, and operator. So the field N value is typically corrected to a standard energy level, usually 60% of the theoretical maximum energy, and also adjusted for overburden pressure to get a standardized value, often denoted as N160, equation 18.13 shows the correction. These corrected values are then used in the correlations. For example, equation 18.16 relating N162 for sands.
Are there other common in situ tests besides the SPT?
Yes, several others are frequently used. The cone penetration test, CPT, is very popular, especially in Europe. Figure 18.13 shows a cone. It involves pushing an instrumented cone-tip probe into the ground at a constant rate and continuously measuring the resistance at the tip QC and the friction along a sleeve just behind the tip.
CPT advantages over SPT.
Advantages include providing a continuous profile of resistance, unlike the SPT's discrete measurements, being faster and often more repeatable. CPT results, QC and the friction ratio, RF SSQC, can also be correlated with various soil properties like soil type, friction angle, undrained strength, equations 18.29 and 18.3, and even OCR and compressibility. Another valuable test is the pressure meter test, PMT, figure 18.1. This involves expanding a flexible cylindrical probe radially against the sides of a borehole and measuring the pressure required for expansion. It directly measures the in situ stress-strain behavior of the soil, providing parameters like the pressure meter modulus, equation 18.21, and limit pressure, PL, which relate to stiffness and strength.
What about investigating rock?
When investigating rock deposits, we use rock coring techniques, usually with diamond-studded rotary drill bits, to obtain cylindrical core samples. The quality of the recovered rock core is assessed, partly using a measure called the Rock Quality Designation, RQD. RQD is the percentage of the total length of core recovered that consists of intact pieces longer than 100 millimeters, 4 inches, equation 18.34. A higher RQD generally indicates better quality rock, equation 18.35 relates RQD to quality description.
And all this information from boreholes, sampling, lab tests, in situ tests gets put together how?
All the information gathered from the field exploration and laboratory testing for a specific borehole is typically summarized in a document called a boring log. Figure 18.16 shows an example. The boring log provides a visual representation of the soil profile encountered, descriptions of each layer, sample locations and types, groundwater level, results of in situ tests like the SPT-N values, and sometimes results of basic lab tests. It's a critical communication tool for geotechnical engineers.
Wow. Okay, we've really gone deep into the principles of geotechnical engineering today. From the very beginnings of soil formation, understanding particle sizes and shapes, plasticity, structure, weight-volume relationships.
All the way through compaction, permeability, seepage, stresses in the ground, consolidation settlement, shear strength, lateral earth pressure, slope stability, bearing capacity.
Landfill liners. And finally, how we investigate the ground with subsoil exploration.
It's a huge field.
It really is.
Yep.
And it's crystal clear that having a solid grasp of these fundamental concepts, drawing from resources like the principles of geotechnical engineering we've been referencing, is absolutely essential for tackling any construction or civil engineering project that interacts with the ground.
Absolutely. You really can't overstate its importance. Whether you're talking about the stability of the tallest skyscraper, ensuring a highway doesn't sink, preventing devastating landslides, or protecting groundwater from landfill leachate, the principles of soil mechanics and geotechnical engineering are right there at the heart of it.
The ground beneath us is anything but simple, as you said at the start.
Far from it. And a thorough understanding of its behavior is critical for designing and building a safe, resilient, and sustainable infrastructure for everyone.
It truly makes you appreciate all the unseen engineering that goes into the world around us, doesn't it? Maybe next time you see a big construction site or even just walk across different types of ground, you'll think a bit more about the fascinating world of soil mechanics happening beneath your feet. And perhaps you'll find yourself wondering about a local project or a natural geological feature nearby. What kind of soil is likely there? How might it behave under load or when saturated? What challenges might the engineers have faced? Suddenly, the ground becomes a whole lot more interesting when you start looking at it through this geotechnical lens.